In this video, we're going to be talking about how to name acids and also a little bit about molar mass. So what is an acid? Many definitions of what acids are for our purposes this unit. We will use Arrhenius's definition, in which he stated that an acid is a substance that produces hydrogen ions, H+, in solution. So if all acids produce hydrogen ions in solution, what must all acids have? They have to have a hydrogen plus. And what is a hydrogen plus? So that just means that we have a hydrogen that has lost its one and only electron. So essentially, this is why we sometimes call acids proton donors, because hydrogen does not have any neutrons. It's a proton and an electron. So if it loses that one electron, it is now essentially just a proton. So acids will be discussed in greater detail next semester. For this unit, we are just going to learn what acids are, some properties, and how to name them. The kind of opposite of acids are bases. So once again, there are many definitions of what bases are. For our purpose in this unit, we are also going to still use Arrhenius's definition, in which he stated that a base is a substance that produces hydroxide ions, that polyatomic ion OH- in solution. So if all bases produce hydroxide ions in solutions, what must all bases have? Duh, hydroxide. Then this brings us to salts. And I know when I say salts, you're thinking of good old sodium chloride, the delicious stuff we put on our French fries. But salts are actually any ionic compound that produce either hydrogen neither hydrogen nor hydroxide ions when dissolved in water. So lots of different things qualify as salts by a chemical definition. So when an acid and base react, they actually produce a salt. Once again, not necessarily good old sodium chloride, just a salt and water as their products. We're going to get more into that in our next unit. So what are some of our properties of acids? So they will have a pH of less than 7. So 0, 1, 2, 3, 4, 5, 6. They produce a hydrogen ion in water. They taste sour. For example, all of that sour candy that you love tastes such because of an acid called citric acid that is in most of those delicious sour candies. When they react with metals to produce hydrogen gas. If you put most metals inside acids, they will bubble, and those bubbles are hydrogen gas. They are electrolytes, which I know is a word that we have used before, but in case you forgot, it means that they conduct electricity when dissolved in water. They will also turn indicators different colors. There are a whole bunch of chemical indicators out there that can react when you have an acid. So indicators are paper or solutions that change color based on the properties of that substance being tested. Once again, we're going to get more into that in our second semester. And as previously mentioned, acids will react with bases to produce salt and water. So what about our bases? What are their properties? They will have a pH of greater than 7, so 8, 9, 10, 11, 12, 13, 14 being our top. They produce a hydroxide ion in water. They are going to taste bitter and feel slippery. The most common example of a base that you are familiar with is soap. Hopefully you've never eaten soap, but if you have, you noticed it had a really bitter taste, and that's because it's a base. It's also why soap feels slippery. They are also electrolytes, meaning they conduct electricity when dissolved in water. They also turn indicators different colors. And they react with acids to produce salt and water. So a lot of similarities in their characteristics. So let's talk about our rules for naming acids. Acids are kind of like ionic compounds in that there are different rules depending on what type of acid you have. Just like an ionic, our first type of acids are binary acids. And these are made up of two elements, one of which has to be hydrogen. The other element is going to be one of those other wonderful elements from the periodic table. And in order to name the acid, we add the prefix hydro, which is acknowledging the hydrogen. Then the suffix, which means at the end, ic, which is going to be attached to the root name for the element, and then we add the word acid at the end. So for all binary, meaning only composed of two elements, we follow the hydric blank ic acid. There is only one exception to this, and that is HCN, which you know from your polyatomic ion chart. CN is cyanide. And technically should be a ternary acid because it doesn't just have two elements, it has three elements, hydrogen, carbon, nitrogen. But it is the exception in that we still name it like a binary acid, and it is actually named hydrocyanic acid. So an example of this naming, we have HCl, which would be hydro, and then the Cl would be chlorine, but we use its root, chlor, and then we add the ic ending, chloric, and then the word acid. So what about HBr? Hydro, and then bromine becomes bromic acid. See, binary acids aren't that bad. Now, as far as our ternary acids contain three or more elements. One of them is still going to be hydrogen. The other part is going to be a polyatomic ion. Now, you know polyatomic ions contain at least two elements in them. So this is where things get a little tricky, just like they did in our ionic unit. So they're named with the suffix ic or us. So when anions name in ate, the suffix becomes ic, so sulfate, phosphate, carbonate. We hack off the ate and change it to an ic, so sulfic, phosphic, carbonic. When the anion ends in ite, sulfite, phosphite, carbonite, the suffix us is used in the acid name. So sulfite becomes sulfus, etc. But just like before, then we will add the word acid to the end. Note, we are not using the word hydro. Ternary acids do not use the word hydro. Now, I refer to ternary acids as having adic-itis, the dreaded chemistry disease, because ate becomes ic and ite becomes us. So adic-itis is how I remember what to do. Once again, HCN is the only ternary acid that is named like a binary acid, hydrocyanic acid. All of our other polyatomic ions are going to follow these rules. So for example, H2SO4, so our anion is sulfate, that is what SO4 is, so I'm going to change the ate to an ic, and it becomes sulfuric acid. Meanwhile, if I had H2SO3, the anion is sulfite, SO3, and ite becomes us, so this is sulfurous acid. So what about H3PO4? All right, so PO4 is phosphate, and therefore ate becomes our ic, so it's going to become phosphoric acid. Similarly, H3PO3, PO3 is phosphite, so ite becomes us, so it's going to be phosphorus acid. See how simple that is? So all you have to do is determine if it is binary or ternary. Some examples for you. Name the following acids. All right, up first, it's the one we keep talking about, HCN. So it's ternary, but that's that one that we keep talking about. So it's the exception, so we're going to give it the prefix hydro and the suffix ic, making it hydrocyanic acid. It's the only exception you have to worry about. What about H2S? So that's a binary one. So we're going to give it the prefix hydro and the suffix ic, making it hydrosulfuric acid. HC2H3O2, it's going to be ternary. The ion is acetate. Ate ending becomes ic, meaning we have acetic acid. HNO3, that is going to also be ternary. NO2 is nitrite, so ite becomes us, giving us nitrous acid. See how simple that is? And let's not forget, this one always gets students, H2O, they want to start telling me they have hydroxyic acid, but it's just good old water, even though it starts with an H in front. We'll get more into that second semester as to why water is kind of weird like that. All right. I want you to pause this video and name the following acids. Remember, the first thing you're going to do is determine if it's binary or ternary, and once you've determined that, you're going to name it appropriately. So pause this video and come back when you're done to check your answers. All right. So HClO4, you should have gotten perchloric acid because ClO4 is perchlorate. HClO3, you should have gotten chloric acid because that is chlorate. HClO2, you should have gotten chlorous acid because that is chlorite. And HClO should have been hypochlorous acid because that was hypochlorite. Keep in mind, hydro and hypo are different. You still keep the whole name of the polyatomic ion. Meanwhile, HI is binary, so it is hydroiodonic acid. And HNO3 is nitric acid because NO3 is nitrate. 8 becomes ic for nitric acid. How'd you do? If you didn't do great, rewind the video and watch this part over again because we're moving on from here. So the other part of this is being able to write the formula from the name. That if I gave you the name of the acid, you need to be able to write the formula. It's super simple though. It goes back to just kind of how we did our ionic compounds. So we know that every acid contains hydrogen, so that's going to be one of your two, and then it has the anion. So the second step is to determine the anion. You're going to look at prefixes and suffixes from your acid's name to determine the anion. So look at either that root. You're going to look at that root and determine what it used to be. Then you're going to write the formula in the following format. Hydrogen, and then however many hydrogens you have, and then your anion. So you're going to take whatever the charge of the anion is as the subscript for hydrogen. You're going to write so now, based on that, I want you to write the formula unit for the following acids. Hydrophosphoric acid, phosphoric acid, and phosphorus acid. So hydrophosphoric acid tells me this is binary because it starts with hydro. So that means I just have hydrogen and phosphorus. So I do my crisscross, I'm going to get my formula. Phosphoric acid, ic, remember, used to be 8, so that tells me this is phosphate. So I'm going to cross hydrogen and phosphate. Phosphorus acid tells me I had phosphite, because ite becomes us. So I'm going to crisscross hydrogen and phosphite. When I do that, I'm going to get H3P for hydrophosphoric acid. I'm going to get H3PO4 for phosphoric acid. And for H3PO3 for phosphorus acid. See how simple that is? This brings us to the other part of our video, which is about molar mass. Now, molar mass is kind of bringing back our math, but I know you can handle it. So a mole is a specific quantity of something. We are going to be dealing with moles a lot second semester. So you can think about it as similar to a dozen or a pair. So a mole is 6.02 times 10 to the 23rd of something, anything. Just like a dozen eggs is 12 and a dozen donuts is 12, that would mean a dozen molecules is 12. Or a pair of eggs is 2, a pair of donuts is 2, and a pair of molecules is 2. Similarly, if I said I had a mole of eggs, that would mean I have 6.02 times 10 to the 23rd eggs, and a mole of donuts would be 6.02 times 10 to the 23rd donuts, and a mole of molecules is 6.02 times 10 to the 23rd molecules. So molar mass is the mass of 1 mole of a substance, or the mass of 6.02 times 10 to the 23rd compounds of that substance. It is often called the molar weight or the formula weight as well, but we will often use molar mass. The units are grams per mole, which we write as G/MOL. That is the abbreviation for mole. All of these answers you are going to round to 2 decimal places. So you can have as many numbers before the decimal place as you need, but you can only have 2 after the decimal place. So that means that you're going to need to round appropriately sometimes. So the molar mass of each element is on the periodic table. That mass that you see below each of the elements is the molar mass of that element. So how do we find the molar mass of a compound? So the molar mass of each element is on the periodic table. So if we have hydrochloric acid, for example, the formula is HCl. That means it contains one hydrogen atom and one chlorine atom. So if we look on the periodic table, we see that one hydrogen is 1.01 grams per mole, and we see that one chlorine is 35.45 grams per mole. So we add those two together because they are together in the compound, and we are going to get that 1 mole of HCl equals 36.46 grams per mole of HCl. Let's try another one. This one's a little harder. So if we have sulfurous acid, that's H2CO3. That means I have 2 hydrogens, 1 sulfur, and 3 oxygens. So if I have 2 hydrogens, I take the mass of hydrogen and I multiply it by 2, which gets me 2.02. If I have 3 oxygens, I take the mass of oxygen and multiply it by 3 to get 48.00. And I just have the 1 sulfur, so I just use its mass straight off the periodic table as 32.07. I'm going to then add those 3 numbers together, and I'm going to get that 1 H2SO3 equals 82.09 grams per mole of H2SO3. Now I want you to pause this video and determine the molar mass of the following: HBr, H3PO4, Al2SO43. Pause this video and come back when you're done to check your answers. All right, let's see how you did. So for HBr, we have 1 hydrogen at 1.01, and we have 1 bromine at 79.90, so we get 80.91. For H3PO4, we had 3 hydrogens, each at 1.01. We had 1 phosphorus at 39.97, and we had 4 oxygens, each at 16, so we should have gotten an answer of 98.00 grams per mole. Now, Al2SO43 was a little tricky because if you remember, the subscript 3, that one right here, is distributed to the S and the O, everything in the parentheses. So we did have 2 aluminums, but we had 3 sulfurs and 12 oxygens. So we find the values off our periodic table and multiply them appropriately, and you know you got the correct answer if you got 342.17 grams per mole. How'd you do? Hopefully you did well. Come to class tomorrow, ready to practice with our acids and our molar masses.